So our next instructor is Kathryn Bywaters, who's a program manager at Honeybee Robotics. She got her PhD at University of Reno in environmental science some 7 years ago. Her interests are more in biology, at least in the past, on what she calls extremophiles, so microorganisms that live in extreme environments, such as extreme heat and cold, and has been to various places on the Earth where you could find them. So she's now working on the management and development of a lot of flight technologies with Honeybee Robotics in Altadena, California, which specializes in robotic systems for the world's toughest environments. And in a way, she has quite a difficult assignment here for the short course, which is to give a presentation on sample capture. So, Kathryn, it's all yours.
Thank you so much for that introduction. Let me start sharing my screen here. And I do have to say thank you so much to Michelle as well for so effectively communicating what's been needed and expected throughout this process. I'm really looking forward to the entire workshop. For this short course, I'm going to go over sample collection, specifically drilling, and introduce you to some of the considerations and thoughts and different mechanisms of drilling, and then sample handling, and then considerations overall for sample collection. Also then going to get into some sample collection examples, specifically the Martian Moon's Exploration Mission, MMX, as well as Mars Sample Return, and then Venus Past and Future. I wanted to give you a variety of the different sample collection strategies in a mission context so that you can see sort of some of the trades that need to be done, some of the aspects that you need to consider, and we'll go over all of those in more detail. So just some general thoughts and considerations. If you see here the little diagrams on the right, first you have that sort of nested hierarchy of sampling system requirements, mission goals, and that's really not an accurate depiction of how you should be thinking about sampling systems. It's more of this Venn diagram of an iterative process that really looks and incorporates and communicates with all of the different aspects. You know, it's highly iterative, and it has to start early. It needs to start early in the mission formation, because really, if there's no sample, there's no mission. You know, that's the whole point of most of, unless it's, you know, unless you're not directly taking a sample, for most of these missions that we're thinking about and wanting to develop, the sample is really the end all be all. And there's a lot of considerations that need to go into how you collect it, how you handle it, and then how you process it. Poorly designed sampling systems do not provide a sample in an optimal state, and that's going to affect your science outcome. A lot of, you know, the current missions to Mars, for example, are focusing on signs of life. And that gets really complicated in how your sampling system is cleaned, what materials it's built out of, and we'll get more into that. But you can see how quickly that develops into, if you're not processing that sample properly, you're not going to get the scientific outcome that you want. And no two missions are alike. And I know it's, you know, a lot of people, I think sample handling has been historically not thought of in some cases, or not truly displayed or shown how difficult it is and how many different requirements go into sampling technologies. So there is no sort of built to print for missions. There's no one sample handling technology that you can apply to all missions. So we do need to identify common approaches and then look at how those can be adapted. And that's one of the reasons why I wanted to show you those mission examples later on. So another key point is there's no substitute for testing under relevant conditions. And one of the things that I love doing is field work. I love going all over the world to really interesting places and testing this technology, because I would say almost 100% of the time, you find and discover things that you didn't know before. Things never quite perform the way that you anticipated or the way that it works on the benchtop. So really testing in a relevant environment is absolutely critical. For Venus, that's a little bit more difficult. It's hard to find the location on Earth where it might simulate all of the parameters of a Venus-like environment, but you can do chamber testing coupled with field testing and really start to tease out where you might have failures of different components or operational scenarios that need to be modified. Also, one thing to think about is planetary protection impacts when sampling. And this really depends on not only the planetary surface that you're going to, but where you're going. So there's special regions on Mars, there's different atmospheres versus the surface of Venus. So there's these planetary protection impacts that you really need to consider, and you need to consider them early on because they can drive a lot of the sort of um, engineering processes that you go through and have to think about. And a lot of times in these missions, your sampling system is the only system that requires these sort of planetary protections. So you really need to know where you're going, where that falls in the planetary protection classes, what you're looking for, what you're analyzing. And then the last sort of general thoughts and considerations is be very aware of your requirements. And this is special to me because as a biologist, my background is in biology, and I've moved into instrument development, and this has given me a special appreciation for this because engineers need requirements. They need to know heat tolerances, pressure. They have all of very, very specific requirements that are needed. And a lot of times as scientists translating their needs into requirements, you often have these sort of nice to haves versus must haves. So these need to be identified. And this is why it goes back to point one, where you need to have this iterative process that starts early in the mission. So you're aware of your nice to haves versus your must haves. And these need to be identified and then understanding how, if necessary, they can be rescoped. So it is a very complex process and there's a lot that goes into it. Some of the challenges with drilling and sample handling. So drilling, one of the largest challenges is this geological uncertainty. So we don't know how the subsurface behaves until we get there. I can't stress this enough. The stratigraphy can change on millimeter scale, and this can present huge challenges when drilling. For example, here you have drilling systems have to work with material strengths that span from 1 megapascal to 150. And this is over, you have the addition of depth range that you have to consider with this as well. So it's no small feat. It's this uncertainty that makes testing in sort of your analog environments, your chamber or in the field, absolutely critical to try and tease out the range of these uncertainties that you might come across. It's absolutely a necessity. Also, sample handling. So, once you've done your drilling, how do you process that sample? And that's something that we have a hard time doing here on Earth. Like the little picture, try imagining putting sand in that straw. It can be very difficult. And you've got various particle sizes that you need to consider, and you have to be able to move. You have cohesion. You've got to put it into a tiny cup or a tray or, whatever the instruments are going to be needing down the line. And you can't always rely on gravity. That's not always going to be a parameter that's going to work for you and that you can rely on to move your sample. So it's sample handling is definitely a challenge, and it's very specific to the types of instruments and the analyses that you want to do. So let's get into drilling a little bit first. Shallow drilling, or 4 centimeters, actually a lot of different options exist and have been developed for flight. You have sort of MSL or Mars 2020, which is very exciting. It's this new approach of collecting a sample and then storing it for later. We haven't done anything like this before. And I will actually get into Mars 2020 a little bit more down the line. Rancor and ROPEC, you have these sort of rotary percussive drills that can take cores. So all of these are versions of a drill that are very specific to the requirements and needs of different missions. You have Dragonfly, which is looking for organics. You have Nano Drill, which opens up the possibility for astronauts or small, lightweight rovers or drones. So you have so many different versions that can be developed with different capabilities depending on the mission needs. And numerous approaches have been developed for solar system bodies. So these small sort of shallow drills, small as in the centimeter, sort of what they're able to excavate, we have a lot of this technology that has already been very well developed. Sort of the mid-range drill, so 1 meter plus. A good example of what's been developed here is the Trident Drone. It was originally done for the Mars Icebreaker mission. The PI was Chris McKay on that. I was considered for the Mars Polar Science and other missions. Here you've got a picture of Icebreaker with the drill. And then here on the right, you actually have the outline of the drill schematic. This drill is actually part of the Polar Resources Ice Mining Experiment 1, Prime 1, and Viper. So this is going to go to the lunar surface. You can see a sort of diagram there of what it's going to accomplish. So it drills down into the regolith. Sample is then extracted in 10-centimeter bites. And that the sample, that 10-centimeter sample, is then interrogated by either mass spec and near IR spec, so Nervous or M solo. And so those casings brought up in those 10-centimeter chunks can actually be investigated in situ. And this is a great example of a mid-range drill. Another mid-range possibility is PVEX, which is the planetary volatile extractor. So again, this is changing our technology and modifying components of our existing technology, or even inventing new technology to get at specific science questions. So if you want to specifically look at volatiles, PVEX, that's what PVEX is designed for. So it delivers volatiles, pretty much melts ice in the core before boiling off, offers the opportunity for additional in situ science. So as you can see there, the core is inserted into the regolith, and the volatiles are then boiled off and can be, you see in the picture on the right, the balloon that captures the volatiles. That's just to show that, that it does work. That gas can then be, those volatiles can then be transferred to whatever instruments are on board and then interrogated. So a lot of this technology is adaptable for whatever science considerations and concerns that you're interested in. And I do have some more examples of that a little bit later as well. So for deep drilling, this is so your tens to hundreds of meters. There is technology out there for that. It's less developed for flight missions, but not to say that there isn't technology that can be used if you're interested in deep drilling. You have cable suspended drills, and that has its pros and cons, of course, like all of them. So you have low mass and power, but you need to have a stable borehole. And this is often used in Antarctic ice coring, and it's also been tested in Greenland. You can see there how big that system is. That's in the tent. You can see the person for scale. So it's it's low mass and low power, but you do need that stable borehole so it does work well in ice. You have drill strings with drill pipes. So the drill system is above the hole. However, your mass and power and it's a lot of mass, a lot of power, and complex robotics. An example of this sort of drilling technique is ExoMars. And then you have the coil tubing drilling. This is one continuous drill pipe. It does require mass, power, and complex robotics. This is often used in oil and gas, and it's being developed for red water drilling. It's a sort of in situ resource utilization for Mars. You can see here sort of the spool on that picture all the way on the right. That green spool is the line, the coiled tubing as it's extended. So these are some of the technologies that are being developed for these deeper drilling missions, but they have a long way to go. If you look back to the shallower drills that have flown, they have flight heritage, but these are under development. One thing that also I think is really important to stress is that drills are actually integrated. It can be integrated instruments, right? So the Trident drill, you're actually getting geotechnical properties of the regolith. You can get ice concentration, physical state of the ice, thermal properties. You can get thermal gradients, thermal conductivity, heat flow. You have the heater and temperature sensor actually integrated into the drill. So you're actually getting science data while you're drilling and collecting your sample. And then Watson is a life detection drill, and this is actually integrating your science instruments into the drill. So instead of bringing the sample to the instrument, you're bringing the instrument to your sample. And this is really revolutionary because you don't have to compromise your sample integrity to get that science return. You can look at your stratigraphy is preserved on a sub-millimeter scale, and then there's a range, a suite of different instruments that can be integrated into your drill bit and provide this the scientific return in situ. So sample handling. Fine. So once you have your drilling or just doing like scoop samples of the surface, sample handling is not by any means something that's easily executable. You have cohesion, adhesion, particle size, metering, cross-contamination, a lot of different things to think about. If you see you've got clumps and fines mixed together, you have fines just in the image there to sort of represent the range of different samples that you can look at. You can either be moving them to a tray, to a small sample cup, to a large sample cup, and then be doing different things with them. So you can look at them in situ right there. You can heat them up, sort of your GCMS approach. You can dissolve them, look at ions, sort of your WICL, your wet chemistry approach. So there's a lot of different analyses that you can do. And what you want to do is going to, determine what format you need to switch those samples into. Are you going for a tray, for a sample cup, for a large cup? So there's a lot of different considerations, and each one of those presents its own unique challenges. So you can have a scoop of surface regolith. You can have a powdered bit for drill cuttings. You can have pneumatic for powder movement. So here we have the scoop, I think that a lot of us are very familiar with. But then there's also this powdered bit for drill cuttings with sort of a viewing window. And we'll get more into that. I'll show some more pictures of that a little bit later. But that you can do some in situ analysis as well with that 1 millimeter screen there. So you can actually see the powder or the core that's been collected. And then another technique is sort of this pneumatic powder movement. And this doesn't rely on gravity or complex of moving parts, you can have that incorporated with a drill or just by itself. But how it, and I think I'll go into the next slide because I have a little bit more detail on how this works. Here we go. So gas is used as a boom to loft material. You can see the spray, the yellow arrows with the spray showing that the gas then hits the regolith, lofts the material up. And in vacuum, the gas is like an explosion, right? So it's quite effective in a vacuum. And this has heritage. There's uses in cold gas propulsion components that have flight-proven components. The sampling head and delivery is mission dependent. So the TRL is low to high, depending on which one. So once your sample is lofted, it's then transferred. And this is one of the beauties of the system as well, is your instruments don't need to be co-located with your sampling. You can transfer that sample to pretty much any portion of a lander or a rover that you would want for sample capture and then distribution to your instruments. So Planet Vac on CLIPS landers uses a catch can. You have the Jaxa's MMX, which is this momentum separator. So you can choose and select particle sizes as well if you like. Dragonfly uses this deflector mode to catch samples. So you have versatility in your sample capture as well. So your transfer, your capture, there's a lot of different adaptability and a lot of different approaches. So this goes back to when I mentioned earlier that you have, you don't have one end all be all sampling tool or technology, but you have you can do a common approach and then adjust and modify based on the mission needs. So this is a simple operation. The actuator opens a valve. It's a short sampling time. There's no ground in the loop needed. It's gravity agnostic, so it works with somewhat cohesive samples, and you don't need to rely on gravity to move or transfer those samples. Again, the sample delivery location is independent from the acquisition location, which gives you a lot of versatility. And you can have clean transfer lines between sampling to reduce cross-contamination if you wanted to have this, say, on a rover with extended sampling down the line. And it does work with a very wide range of sampled particles. So again, this is an approach that then can be adapted to a range of different environments. Here is a video on the Zodiac test there. You can see this was done to show that the system works under the landing conditions, the temperature, shock, vibe, all of that with actually landing and still operating. And you're able to collect hundreds of grams of sample for this. This can also be coupled with a drill. So you can collect surface sample as well as a sample with depth. The drill will bring the sample to the surface. The stratigraphy can be preserved. You can do it in different, say, 10-centimeter chunks if you would, and then look at how the sample varies with depth. That can be delivered to instruments, instrument suites. This picture up top, it shows it on the foot pad of a lander with the drill integrated into the foot pad and Planet Vac, the pneumatic system on top of that foot pad. But it's also versatile enough that it could be its own addition. It doesn't need to be the foot pad. So again, you're seeing that sort of theme of versatility and adaptability with these sample collection and sample handling mechanisms. Sample handling for cores. Cores can pose a specific, a unique problem all to their own because you kind of never know what you're going to get. You can have intact cores, you could have several pieces, you could have it mostly broken up. So you need to be able to deal with a wide range of these cores. And you have some options. So you can do seal and return to Earth like Mars 2020. You can analyze in situ with like micro CT here, where you can actually take sort of get snapshots of thin sections within that stratigraphy. You can crush it into powders for further distribution to different instruments, such as in ExoMars. Here is that preview bit that I had discussed earlier, where you actually have that slot so you can preview the bit in situ and look at that core, look at the stratigraphy in that core and analyze it right there. You can also do subsampling where when you have the core, you can then look at specific chunks. So again, adaptability for what the sort of mission scenario is and what the science questions are. So just some other considerations when thinking about sample collection and handling. So location, 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 right? We know that with different locations come specific constraints. So your constraints for Mars or an asteroid is not going to be the same as for Europa, for Venus. They all have temperature requirements, radiation requirements, and all of those need to be considered. And you need to also know what analysis. You need to be very specific about what analysis and what sort of science questions and science return you want, because your constraints on a sample handling process is not going to be the same as for geology, as for biology. For geology, you might want to really maintain that stratigraphy in the sample. For biology, you're going to worry about contamination and, are you going to want to do sort of dry heat microbial reduction? Or do you need something that will really clean off any organics? Or are you looking for volatiles and you need to come up with a strategy for hermetically sealing your sample? So there is a wide range of considerations that you have to look at when you're devising your science goals and how you're going to go about answering that through sample collection. It's going to drive your material selection, your collection strategy, your sample handling process, your storage conditions. So your packaging of your sample has to meet these stringent science-driven, not just contamination control requirements, but requirements in general. And that's, again, going back to that sort of first thought of it needing to be this iterative communication that begins early in mission development. And that's going to drive your physical architecture and your hardware implementation. For planetary protection, in most cases, your sampling system is the only system that touches those special regions. So for Mars Phoenix, the forearm shown there is the only thing that was concerned for planetary protection, but it was just simpler and more cost-effective to treat the entire arm and put it inside the biobarrier. Also for Watson, for the life detection drill, adding a cleaning station to clean that drill prior to entering the subsurface, that would greatly reduce the sort of the complexity and minimize your potential for false positives. Another thing that so this is very important to incorporate, and Mars 2020 has done a really good job of having witness plates incorporated. So those are passive getters that are going to let you know what the background level of contamination really is. And these are specific, again, to what you're looking for. Are you looking for volatiles or organics? Because then you might want to use sort of an aluminum or silicon wafer. Are you looking for particles? Do you want to be able to do microscopy, then maybe a polished gold? So there's a lot of different considerations that come into play with not only sample collection and sample handling and processing, but also ensuring that that path that you laid out, you can characterize any background contamination or sort of levels of these particles in the environment. Again, analog field testing is critical. I just really wanted to drive this point home and have its own dedicated slide here. From a geotechnical perspective, Mars is very similar to Earth. There are a number of locations that are good analogs for Mars. There are, if you're thinking about Venus, there's tons of different basalts and drilling locations. You're not, of course, going to get those high temperatures, but that's where the chambers come into play. And this really allows you to get at the geological uncertainty so that you can understand the challenges of collecting samples in these environments that don't necessarily come up in a laboratory setting. So getting into a couple of examples with the few minutes that I have left. So there's the Jaxa mission with contributed payloads from NASA and ESA. And the goal is to return a sample from Phobos, which is one of the moons of Mars, do a flyby of Deimos, and then monitor the Mars climate. So the science goal of this mission is to determine whether the Martian moons are captured asteroids or result of a larger body hitting Mars, potentially more like our moon. There's a suite of different payloads, won't run through all of them, but really what I really like about this is the sampling system. So there's actually two different sampling systems. There's the core sampler and the pneumatic sampler. The core sampler will push a tube deployed using an arm during a 2 or 3 hour period on the surface and collect a core sample. Whereas the pneumatic sampling system will again use that compressed gas system that I showed earlier and collect sort of the younger regolith on top. So not only does it provide mission redundancy, but you can also get the two different types of sample. You can get the potentially older core sample where you can see the stratigraphy, gain more insight of potentially the processes that have been happening on the surface, that younger regolith compared to sort of an interior core. And I think this adds a lot to the science return. It allows us to really compare different samples and ask some of those questions that we might not get from like an N of 1 sample, right? Just having one core, one regolith sample. For Mars 2020, this is very impressive when we look at sample collection techniques and handling. I don't think we've really ever seen anything like this before. It's going to collect rock cores and regolith samples, packages these materials into hermetically sealed sample tubes, deposits them on the Martian surface for potential return to Earth. And it really consists of these two robotic systems. So you have this outside arm and turret, and on that turret you have the coring drill as well as some other instruments. And then inside the rover, you have this adaptive caching assembly. And with sort of in between the two, you have this bit carousel as part of the adaptive caching assembly. And that really takes the samples in and then stores them in the adaptive caching. So it's very intricate. It's really an impressive feat of engineering, I would say. The stringent planetary protection and contamination control requirements were levied on that adaptive caching assembly. One of the science objectives is to look for signs of life, right? So you can imagine that there's the planetary protection, but also the contamination requirements that are so heavily weighted on this system. And that drove design and material choices. Also your specific hardware handling techniques. So this really, again, drove the physical architecture and the hardware implementation with setting your requirements such as 10 ppb of organic carbon and 1 terrestrial viable organism per sample. So Venus, last but not least of sort of the examples. Exploration of Venus. So Venus and Earth are very similar in size. We've heard a lot so far of the contacts of Venus just in the last couple of talks. Venus's atmosphere consists mostly of CO2 gas, which has been traps heat, sort of the runaway greenhouse effect, and is, the surface we believe is inhospitable to life as we know it. On Earth, the carbon in the atmosphere is regulated in a global cycle that maintains sort of the balance that supports life. So understanding the reasons why Venus has had this evolutionary trajectory would really give us insights into possible scenarios for Earth and the way Earth has been able to maintain this balance and where sort of the tipping points are. So Venus has a lot of interest for moving forward. And I know I'm running getting a little bit short on time, so I'm going to move quickly through this material because I think it is important that everyone sees this. So the Soviet Venera 13 and 14 were landers that completed in situ soil analysis experiments. This again was sort of unprecedented for that time, and really displayed what is possible on another planetary surface. You had a soil sampling drill, which was capable of drilling 3 centimeters in 120 seconds, a pneumatic sample transport system, and then X-ray fluorescence spectroscopy instrumentation. This is some of the missions. The red ones had a sampling system that didn't work. The 3 in green had sampling systems that did work. Just to point out the survival time here, the goal was for the Venera missions were 32 minutes, whereas they lasted for quite a bit longer. But the survival duration was linked sort of to a time window that the relay spacecraft flyby was in. So we don't really know the capabilities of this hardware in the look of sort of survival times and what's possible. This was the drilling operation. So you have the boring, which the electric motor starts, actuates a ball detent, it falls to the ground and starts drilling. Then you're going to load your sample. So at 120 seconds, you have this pyrotechnic charge that's set off, and that draws air in. Your internal pressure inside the tubes is 100 kilopascals. That falls into the soil receptacle. Your second pyro is actuated. The airlock to the soil feeding mechanism is closed. And then at 188 seconds, you have that third pyro is actuated and pierces the membrane to the vacuum chamber that's on board. And that pressure drops from 9 megapascals to 5 kilopascals. And then you have a transfer of the sample to the XRF. And that is by the 4th pyro charge, which is then the soil is then sort of sprayed through a window. And this was back, in the late 70s, early 80s, and really just demonstrated what we're capable of in such a harsh environment such as Venus. And we see the sort of the terrain here. We have 13 on the top, 14 on the bottom. 13 is this orange, brown, flat bedrock. I'm going to go ahead and skip through this a little bit, just because I know we're running short on time. What types of rock? We were actually able to get a lot of information from the drill, from the XRF, from the regolith, the penetrometer and regolith odometer, and also the parachute. So the parachute failed on Venera 7, but with the Doppler shift at impact at the surface, we could tell that it was harder than sand, but no harder than pumice. So there's a lot of different instrument suites that we're working together over these missions that allows us to understand the types of rocks and the type of terrains that are present on the Venus surface. A couple of things that came out of this was the high pressure devices. So you have to have the soil sampling drill that can work or high temperature devices. New heat resistant materials and electronics had to be developed for this. Exotic lubricants had to be developed for this. And I think one of the impressive things as well is that the machine parts were designed to fit and function properly only after thermal expansion to 500 C. So again, it's looking at the environment, looking at the parameters, and adapting accordingly. So sort of the new and fun stuff that's coming up for Venus Drill is high temperature technology for the Venus In Situ Explorer mission. It's a rotary percussive drill that can do 5 centimeter depth, 4 millimeters per minute. It has a pneumatic transfer system, suction based, similar to the Venera sort of pneumatic system that we were just talking about. And end-to-end testing has been performed in the Venus chamber. So you have this high temperature technology, the planetary gearbox, motors, sensors. The whole rotary percussive drill is mounted to the lid of that Venus chamber, and then it's all inserted into that Venus chamber. You can see the picture there. This is no easy feat. This is quite extensive to do. That drill has to be mounted to the lid with wired electrical feed throughs. The lid needs to be placed and the drill suspended inside the chamber that's then filled with CO2 at room temperature. It needs to be checked for leaks. The chamber then needs to be heated to 460 C, which can take days. The pressure will rise. You need to vent periodically as CO2 reaches that critical point, and then drilling tests are performed inside the chamber. So it's quite an extensive process. This is just a movie of the drill. I'll show it just for a second, so you can see how it works. Sorry, skipping through quickly. And then just is again, just showing some of those testing parameters. There's another look at the chamber. You can see that the motor temperature over time stabilizes. Your drill depth over time, you're able to reach that 5 centimeters. You actually get these fine grains generated, which in the drilling video, you can see some of those fine grains around the hole. And then here's the 2 centimeter hole that you're able to accomplish. These are just conclusions based on what we had discussed. I will leave those up and then stop presenting at this point.